Hello, this is Dr. Christy Patton-Lokes, a chemical engineering professor at Missouri S&T. We're continuing to look at separation systems, and we are at this point in chapter 12 out of the Turton textbook. So they talk about how you would like to sequence distillation columns. So the first thing that you want to do when you get a set of components that you're wanting to split is first find like boiling point data to order them based on volatility, and then look at the relative volatility for each combination pair in order as you go down this list. What you want to see is that all of the alphas where you want to make a split are always greater than at least 1.05. The larger they are, the better. You're also going to want to verify that you don't have huge reboiler duty, because if you're putting that much heat in, it's going to cost so much to operate, your plant may not be economical. You also want to keep an eye on your tower pressure, because you can end up getting near the critical temperature, and any little upset to the system can push you to the point that you are no longer able to get that two-phase split by boiling. Be sure your column pressure drop is okay. You don't have as much room to work with if you're under vacuum, so again, keep an eye on that. The overhead vapor needs to at least be partially condensed in the top, and you'd rather do it with like cooling water and avoid having to do refrigeration. If you do have to do refrigeration, then keep an eye on that to make sure it's a small quantity. The bottom's temperature needs to be low enough, well, it will be high, so I guess not so high, that chemical decomposition will occur. You also want to make sure that azeotropes are not going to get in the way of the separation that you're wanting. Now, we can deal with azeotropes. We'll look at that in the next lesson. But they, are something to keep an eye on early on. When you have a number of product streams that you're wanting to produce, you end up with a lot of different ways you can sequence the separations for just simple distillation. So when you only have two components or two products that you're wanting to achieve, there's only one way to do it. One tower will do it. But if you have, more products, then you end up with more ways of doing it. And so this formula here tells you what that is. And you see that it doesn't take long before the number of options grows to a huge number. And so we would like to be able to make good, wise, economical choices without a lot of extra work. So we want to go back and use some heuristics and best ideas on how to make good choices. So in a series of 4 components, notice that they're listing here the compounds A, B, C, and D in order of volatility, so the most volatile on top, the least volatile on the bottom. And then they use a line to separate where they're going to split. Everything above the line is going to go in the top, everything below the line will go in the bottom's product. And you can't just like pick out and say, oh, I'm going to take B out first. That's not possible. It has to be, say that A or maybe A and B would go out the top. Now they call it the direct sequence if they're each time taking out the most volatile, and they call it the indirect sequence if each time they're taking out the bottom's product as they're sequencing. These others are all various combinations. So let's look at this one in the middle here with detail. So they started by doing a split, so A and B are going to go out the top and C and D out the bottom. So the split is going to be between B and C, and the ease of this separation is going to be based on the relative volatility of B and C. But now then they're just going to have 2 binary mixtures that they need to split. And so they'll do those. And they have various combinations of this. So the best sequence some sort of, again, these rules of thumb or heuristics. So first you would probably want to remove anything that's thermally unstable, corrosive, chemically reactive early, because those are your troublemakers. They're going to have a lot of special care in the separation sequence, special materials perhaps. And so if you can remove them early and isolate them, everything else will be easier. Now, sometimes the easiest, most simple-minded is the best, and that is just simply to remove the final products one by one as the distillate or the bottoms product. That's called the direct or the indirect sequence. But maybe you can be a little bit wiser than that. So frequently we sequence the separation points where we draw that line so that we end up with a split that's fairly close to equimolar in the distillate and the bottoms product. That is going to, have some advantages in terms of the sizing of the equipment. If we sequence the separation points in order of decreasing relative volatility, then you would like to do the easy splits first and the hard splits later. So look for the relative volatility values that are much greater than 1 and do those early. The ones as they get closer to 1, do those late. If you have something that you need to have a very high purity, probably that one is good to do late in the sequence. And again, favoring nearly equimolar splits of distillate and bottoms. The only thing to be aware of here is just making sure that the reboiler duty isn't too high, because that's a large operating cost in the plant. So they do this example in the textbook here. And we won't go through it with great detail, but they do relative volatility information for everything in this mixture. They're ordered from most volatile to least volatile. And these are the flow rates of these. So you see that there's a small tweaky amount of propane. Butanes and pentanes are, roughly, there's more pentane than the others. So these are the relative volatilities. We've got large relative volatility for C3 to IC4 and for NC4 to IC5, and fairly small relative volatilities for the iso and normal alkanes. All of these were going for 98% recovery, so there's not a purity advantage to any of these. And so they discuss in the book some pros and cons of various things, but doing easy ones early on is nice. Doing this split here makes it so that everything's equimolar, so you have two smaller series that you're working with from there. So I might choose to do this one first and then come in and do this next. But you also might just say, oh, that one's going to be so easy, I'll just do it early. So this is, one of the many possible solutions to this. And so we want to consider, all of our options, but simple distillation isn't really our only option. Sorry, my slides aren't advancing. So if you had 3 components, there are several ways that you can split them. The first is just the direct or indirect sequencing, where you're just always removing one product at a time and focusing on that. And those two are shown here. And those are simple, but we can also do more complex methods. So, I'm trying to, there we go. I got my slide to stop there. This one has a side rectifier or side stripper, depending on whether you're doing it out of the top or the bottom of the tower. But what you're doing is once you get it to being mostly A plus B or mostly B plus C, you're taking out a side stream and then sending that through another column, which produces the pure B. Now, this may be more economical because you're taking advantage of the energy already in the tower, On the other hand, it may be more complex to operate, and so you may spend so much time with operators messing with it that it isn't a good plan. We also can just simply take out, maybe you get enough purity at some point that you can take out a side stream. Remember, if you're only going for a kind of a mediocre purity, then maybe you can get the side streams. And so look at your separation and what is going on inside the tower at all points in time. So we've looked at several different possibilities for ways we might sequence separations, some very simple and straightforward, some much more complex. We want to come back and take a systematic way of evaluating them in the next video lesson. Thank you very much for your time.